last lecture, we discussed about basic probability concepts. In this lecture, we will introduce the concepts of random variables and how to characterize them. A random variable is basically a number assigned to the sample points, so that we can numerically analyze the data. Let us see the definition of random variable. Consider a probability space S f p. A function x from S to R is called a random variable if the subset S such that x s is less than equal to small x belong to F for each x belonging to R. So, this is the definition. First of all, the random variable is a function from the sample space S to the real line, but there is a requirement. The requirement is that if I consider any point x on the real line, we can define an event like this S such that x s is less than equal to small x. So, this event should belong to F. This requirement is only for uncountable sample space. This implies that the probability p can be assigned to the event, this event S such that x s less than equal to small x, because we have to define a probability. This probability should be well defined. Otherwise, for a discrete sample space, any function from x to R can be considered as a random variable. So, we have defined the random variable. Now, how to characterize a random variable? First of all, we will define probability distribution function. Now, we know we have defined an event S such that x s less than equal to small x. This is the event. So, the probability of this event is known as the probability distribution function at point x. F x of x is equal to probability of the event comprising of S such that x s is less than equal to small x, and for notational simplicity, we simply write probability of x less than equal to small x. This is also called the cumulative distribution function, therefore, it is abbreviated as CDF. We will introduce also the concept of probability mass function. Consider a discrete random variable with the range. These are the values the random variable can take. Suppose we enumerated them x 1, x 2, x 3, etc. Then the probability mass function, that is denoted by p x of x. So, this is capital X is for the random variable at a value x. It is the probability that x s is equal to x. So, we have to find out all those s for which x s is equal to x. This also, for notational simplicity, we have written probability of x is equal to small x. We will consider one example. Consider the example of a tossing fair coin twice. For the random variable x defined as given below, find f x of x. We have defined a random variable. Suppose tossing a coin, the sample space can h s, h t, t s, t t. These are the 4 members, and we assign 0 to h s, 1 to h t, 2 to t h, and t t is assigned 3. So, therefore, the value of the random variables are 0, 1, 2 and 3. These are discrete values, and corresponding probabilities are given by suppose equally likely. So, probability of x s is equal to 0, that is h s, probability of h s, that is 1 by 4. Similarly, probability of x is equal to 1 is 1 by 4, x is equal to 2 is 1 by 4, x is equal to 3 is 1 by 4. So, we have to draw the PDF. So, for that, this axis is our x and this is my f x of x. So, let us see what happened, because we have to define for all values of x. So, when x is less than 0, suppose, in that case there is no event for which x is less than equal to 0, less than 0. So, that way up to 0 it will be 0 only. Now, if I consider suppose f x of 0, suppose I have to find out f x of 0. So, f x of 0, that is probability that S such that x s is less than equal to 0. So, what will be this event? We know that this is for which x s is less than equal to 0. So, less than equal to 0 means there is only one s, that is h s, that is probability of h s. So, that is equal to 1 by 4. So, this way at this point we will have 1 by 4. Similarly, if I consider up to 1, so for all the probability will be same. So, we will have 1 by 4 like this. So, that way we can complete this CDF plot. Let us see how this CDF plot look like. So, this is the CDF plot. So, x 0, 1, 2, 3, these are the values. Correspondingly, the CDF up to here it is 0, then there is a jump, and then this will remain at 1 by 4. Again at 1 there is a jump, this will become half like that. And finally, this is 1 at point 3, and then henceforward it will remain 1. So, this is a CDF plot for this random variable, discrete random variable given by these values. So, we have seen this plot, and on the basis of this plot we can describe the properties of this CDF. So, if I consider the properties of the CDF f x of x, we see that generally this will be a non-decreasing function. So, number one is that we can say that f x of x is monotonically increasing in x. So, as x increases, f x of x monotonically increases means it may remain constant or it will increase. Number 2, we also observe that f x of minus infinity is, if I extend here up to minus infinity, at minus infinity this value will be equal to always 0. Similarly, f x of plus infinity is always 1. Number 3, we also observe that suppose at this point, at point 1, what is the value of f x of x? That is the value, because while defining this probability we consider capital X less than equal to small x. Therefore, at this point, at point 1 the value is equal to half. So, what does it mean? That f x of x is a right continuous function, is continuous from right. So, that means what is the value of the function at this point? Whatever we get by approaching from the right hand side, that is the value. So, that way these are the properties, and using the distribution function we can completely characterize the random variable. We can find out any probability, for example, probability that x lies between, suppose if I say that x lies between some x 1 and x 2. Okay. So, that probability will be equal to f x of x 2 minus f x of x 1. So, that way we can find out any probabilities involving this random variable x. We will define continuous random variable and probability density function. Now, what is a continuous random variable? If corresponding CDF is absolutely continuous. So, a random variable x defined on the probability space S f p is said to be continuous if f x of x is absolutely continuous, which implies that f x of x can be written in terms of an integral, this integral from minus infinity to x, small f x of u du. So, this quantity, suppose I have a CDF like this, suppose this x f x of x. So, this CDF is like this, suppose it is a continuous, absolutely continuous, that means these variations are bounded. We will not go deep into this concept, but what is important is that f x of x can be expressed as the integral of this density function. So, we can write or we can tell that this f x of x is the probability density function, it is abbreviated as PDF. Now, for a simpler case, suppose this CDF is differentiable function. So, in that case we can write f x of x is equal to small f x of x is equal to d dx of capital F x of x. So, PDF can be expressed as the differentiation or differentiation of the CDF. So, of course, in that case we require that f x of x should be a differentiable function. So, we can derive some property of the PDF. For example, we know that CDF is a non-decreasing function. So, if the PDF is the differentiation of the CDF, then we can easily show that f x of x is always greater than equal to 0. Number 1, it is a non-negative function. Number 2, now the value of the CDF at infinity is always equal to 1. So, from the definition we can easily say that this integration of f x of x dx from minus infinity to infinity, that will be always equal to 1. Also, we can find out any probability of suppose the event, any event, suppose that event is x lies between some x 1 and x 2. So, this probability we can find out using the PDF from x 1 to x 2 integration the PDF f x of u du. So, that way we can find out any probability involving the random variable, continuous random variable x with the help of the PDF. Example of a PDF, it is a very famous PDF, everybody knows it. This is the normal or Gaussian random variable with parameter mu and sigma square. So, these are the two parameters. The PDF is given by f x of x. This is the scaling factor 1 by root over 2 pi into sigma e to the power minus half of x minus mu divided by sigma whole square. So, this is a bell shape. Suppose if it is x, this is f x of x, then around, and suppose this is mu. So, around that, about that we have a bell shape curve like this. So, this is the normal distribution about point mu. This is also will show that this is an important parameter called the mean parameter, and how this spread of this PDF curve will determine or controlled by this parameter sigma. So, that way we define random variable, single random variable. We also define the discrete and continuous random variables, and CDF, PDF, PMF, etc. These are the functions which characterize a random variable. Next, we will go to multiple random variable. Suppose two random variable x and y defined on the same probability space S f p. In other words, x n and y s are two functions defined from S to the real line. So, we have so at every point S we have one function x s, another function y s. So, that we can characterize suppose these 2 points, this point suppose which is mapped from the sample space by the mapping x s and y s. So, all the points can be expressed as the Cartesian product of these two random variables. So, that they can be represented in a plane like this. So, corresponding to this point we will have a point here like this x y. Of course, while defining these two random variables, we take care that the probability can be properly assigned. Now, given the definition of two multiple random variables, we can characterize multiple random variables through some probability functions, just like in the case of single random variable CDF and PDF and PMF. Here also we will define the same. A joint probability distribution function. The joint CDF of x and y denoted by, this is the notation, capital F subscript x y at point small x small y. It is defined as the probability, it is again a probability of the event S consisting of sample element sample point S such that x s is less than equal to small x and this comma means and y s is less than equal to small y. So, this is the probability of those x for which x s is less than equal to small x and y s is less than equal to small y. So, this is the definition. With this definition, we can define what is known as the joint CDF, and this joint CDF characterize the random variable at any point x y belonging to the plane R 2. Okay. Now, what are the properties of this joint CDF f x of y? So, they are derived from the property of the CDF basically. Therefore, we can say that f x of y, it has two arguments x and y. It is so joint CDF f x y at point x y has some properties which are derived from the definition of CDF. So, these are similar to the properties of the CDF of a single random variable. That way, this f x of x y is a non-decreasing function or monotonically increasing function, non-decreasing function of both the arguments of x and y. Number 2, now let us see the event f x y at minus infinity, that will be always equal to 0. From the definition we can say that this is equal to 0. Similarly, f x y at point, any point you consider, any point y, and that is minus infinity y. So, this is the probability that we can say that x is less than minus infinity, that is less than equal to minus infinity, that is always equal to 0, and this is the end, x is less than equal, y is less than equal to small y. So, if we consider the intersection of these two events, we will get the null event. So, that way probability of phi, that is equal to 0. Similarly, we can also show that f x y at any point x minus infinity, that is also equal to 0. So, that way f x y, if any of the argument is minus infinity, then it will become 0. Similarly, if we consider, that is important, number 3, suppose what is f x of x and y argument is infinity. So, this is because infinity means this second argument, that will correspond to the entire sample space. So, intersection of the sample space and x less than equal to small x. So, that way it will be simply equal to f x of x. So, that way this is the distribution of small x. The distribution of the single random variable at point x we can derive from the joint CDF, and this is known as the marginal CDF. As we derive it from the joint CDF, it is known as the marginal CDF. So, the marginal CDF f x of x is obtained from the joint CDF at point x infinity. Similarly, we can find f y of y also, that is f x y at point infinity y will be equal to f y of y. So, that way marginal CDF at point y we can obtain from the joint CDF at point infinity y. So, this is important property. So, that way joint CDF completely characterize two random variable x and y, and from these joint characteristics we can find out how these random variables individually behave, that is marginal CDF in terms of the joint CDF. Similarly, finally, we can find out number 4, that is f x y at point infinity, that will be always equal to 1. So, these are some of the properties, and we can find out any probability involving the joint CDF. We can find out any probability involving the joint random variable x y. So, how we can find out? Let us see. So, we can find out, for example, probability that x lies between small x 1 and x 2, y lies between small y 1 and y 2. So, this probability, this type of probability we are interested to find. Okay. So, using the again from the basic definition, we can show that this probability will be equal to probability that x lies between x 1 and x 2, y lies between y 1 and y 2. So, this is given by, so this is equal to f x y at point x 1 y 1 plus f x y at point x 2 y 2 minus f x y at point x 1 y 2 minus f x y at point x 2 y 1. So, this way we can find out the probability involving two random variable x and y. Next, we will define the joint PDF. Two random variables x and y are called continuous random variables if their joint distribution function is given by this. So, just like in the case of single random variable, here the joint CDF is represented in terms of the double integral of a non-negative function. This is the f small f x y, small f x y at point u v du dv. Okay. Now, this quantity is always greater than equal to 0 and it is called the joint probability density function, joint PDF. So, that way it is joint PDF, joint PDF. Now, if the CDF, joint CDF is differentiable, it is a partial differentiation, doubly differentiable in both x and y, then we can write a joint PDF at point x y is the second order partial derivative del 2 del x del y of the CDF f x y at point x y. So, the second order partial derivative gives the joint PDF. Now, you note that this joint PDF is a non-negative function, it is always greater than equal to 0, that follows from the property of the joint CDF, it is non-decreasing in both argument x and y. Also, we can find out any probability. So, we can find out any probability, for example, probability that x lies between some x 1 and x 2, y lies between some y 1 and y 2. So, this probability we can find out by the integration, double integration of the joint CDF. dV. So, this is integration. So, that way we can find out the any probability involving the two random variable x y, x and y, two random variable x and y using this double integration. Similarly, also if we consider suppose this integration from minus infinity to infinity of the joint PDF du dV. So, that will be nothing but the joint CDF at point infinity that is equal to 1. Therefore, the area under the joint CDF it will be a surface. So, that way the volume under the joint CDF surface will be always equal to 1. So, that way we have defined joint CDF and joint PDF. We introduce also another concept what is known as the independence of two random variables. So, we are discussing about the properties of joint PDF. One more important property we will tell, that is the marginal PDF, how to derive from the joint PDF. So, we know that f x of x is equal to f x y at point x infinity. So, this we can write that this is integration from minus infinity to x. Now, this is infinity. So, that way f x y at point x y dy is from integration is from minus infinity to plus infinity, and then integration with respect to x dx, that is from minus infinity to x. So, now this quantity, this inside quantity is the PDF of x. We can find out the marginal PDF f x of x from the joint PDF. Consider f x of x, this CDF marginal CDF of x at point x, that is given by, I know in terms of the joint CDF it is f x y at point x infinity. Also, this quantity is equal to integration minus infinity to x marginal PDF f x u du. So, this quantity is same as this. Now, this quantity joint CDF at point x infinity can be written by this integration. So, inside integration is from minus infinity to infinity with respect to y, and outside integration is minus infinity to x with respect to x. So, this we can write in terms of now comparing with this, this quantity is same as f x of x. Therefore, what we get is that small f x of x, that is marginal PDF, is equal to the integration of the joint PDF with respect to y. So, similarly, f y of y also we can find out, that is the integration of the joint PDF with respect to x. So, that way this is what is important is that given the joint PDF, we can find out the marginal PDFs, both marginal PDFs. So, that way that means once we know the joint PDF at each point x y, we know all the characteristics of the random variable, including their individual description. So, that is the importance of marginal PDF and CDF in terms of the joint PDF and joint CDFs. Next, we will introduce the concept of independent random variables. We know two events, when two events are independent, that is two events are independent if their joint probability is the product of individual probability. So, same concept is used here. Suppose x and y are two random variables characterized by two. Suppose x and y are two random variables characterized by their joint CDF, then x and y are independent. It is the definition if joint CDF is product of the marginal CDF for all x y belonging to R 2. So, this result should be satisfied for any x y belonging to R 2. So, we have to consider all x y point where this relationship is satisfied, and otherwise it will be called x and y will be called dependent. And in terms of the PDF, joint PDF, we can write that joint PDF is the product of the marginal PDF f x of x and f x of f y of y. Similarly, here the joint CDF is the product of the marginal CDF capital F x of x into capital F y of y. So, this is the definition of independent random variables, and concept of independence plays important role in probability analysis. Let us summarize the lecture. A random variable x is defined as the mapping from a sample space to the real line, with the requirement that the event as such that x s is less than or equal to small x, this event must belong to f. So, that way we define the random variable, and a random variable x is generally characterized by the CDF, that is the probability distribution function or cumulative distribution function f x of x. This is the probability of the event as such that x s is less than or equal to small x. Similarly, we define the probability mass function for the discrete case. In that case, this is the probability that x s equal to x. So, this probability is known as the probability mass function. For the continuous case, we define the PDF probability density function, and this probability density function is related to probability distribution function CDF by this integration. So, f x of x is equal to integration of f x small f x u du from minus infinity to x. So, that way we define the PDF. We also discuss about joint random variables, two random variable x and y. They are characterized by the joint CDF, and joint CDF can be defined similar to the CDF for the single random variable. We also discussed about a joint PMF, Pxy at point small x small y. This is the probability that x is taking x and y is taking y. And similarly, joint PDF that is related to joint CDF through the integration. So, these quantities we discussed. We also discussed about the marginal quantities. The margin given the joint CDF or joint PDF, we can find out the marginal CDF. For example, CDF f x of x is equal to the joint CDF at point x infinity. So, when we put y is equal to infinity, then we will get the f x of x, joint CDF of x. Similarly, PDF of x, that is small f x of x, is given by the integration of the joint PDF from minus infinity to infinity. So, this is the integration with respect to y. So, f x of x marginal PDF is given by the integration from minus infinity to infinity, joint PDF integration with respect to dy. Then we introduce the concept of independence. X and y are independent if joint CDF is product of marginal CDF, that is for all x y belonging to R 2. Similarly, this independence can be defined in terms of joint PDF. So, if joint PDF is product of the marginal PDF for all x y belonging to R 2, then also x and y are independent. Thank you.